patrons of the event. It's a pleasure and an honor to introduce together Dr. Geert Molenberghs. En nombre de las instituciones organizadoras del evento, es un placer y un honor presentar al Dr. Geert Molenberghs. El Dr. Geert Molenberghs es matemático y doctor en bioestadística de la Universidad de Antwerpen en Bélgica. Se desempeña como profesor de bioestadística de la Universidad de Hasselt y de la Universidad Católica de Leuven en Bélgica. Ha sido director fundador del Centro de Estadística de la Universidad de Hasselt y director del Instituto de Biostatistics y Bioinformática, de Estadística L-BioStat de las universidades de Hasselt y Católica de Leuven. Ha sido presidente de la International Biometric Society, fue elegido Fellow of the American Statistical Association. La Royal Statistical Society le concedió la medalla Guy Medal in Bronze en el año 2002. Sus investigaciones en análisis de datos longitudinales, ensayos clínicos, datos categóricos, datos de omisión en estudios clínicos y epidemiológicos, entre otras temáticas, han sido publicadas en cientos de artículos de las más prestigiosas revistas de estadística y medicina, entre otras, y en libros de las más prestigiosas editoriales. Ha sido coeditor de Biostatistics, Biometrics, editor adjunto de Applied Statistics. Bueno, creo que me podría quedar un largo rato hablando sobre la magna contribución del doctor Geert Molenberghs al desarrollo de la estadística. El doctor Geert Molenberghs nos va a presentar la conferencia Handling Negative Correlation and or over underdispersion in Gaussian and non-Gaussian hierarchical data. Thank you very much, Dr. Geert Molenberghs, to accept our invitation.
Thank you very much. Thank you very much for your very kind words and for the invitation and the honor to be with you, although virtually, that's the way we have to do it right now. It's a bit of an interesting day for me because in my morning time, I gave a presentation already in Australia when it was their afternoon, and now we do it al revés, with me in afternoon mode and you in morning mode. So thank you again, and it's great to encounter so many fine Colombian statistical colleagues. And I already look forward to future interactions, of course, when times will be a little easier. What I would like to do in this presentation, and I'm assuming that you can see the presentation well, is start with, and I should actually say that this is work done jointly with several people, including my colleague Geert, is start with a few examples, review some relatively well-known concepts, and from there go towards a few developments in the context of course, hierarchical data with high and low correlation, positive and negative correlation, over dispersion, under dispersion. So the first example is, and some of you may have seen it before, is a preclinical study where we randomize rats, Wistar rats, over 3 groups: control, and then low dose and high dose of decapeptyl, which is testosterone. And the question is whether growth, and in this case craniofacial growth, is depending on testosterone production, yes or no. The data practically are collected by putting the rat under anesthesia. Then with a touch-sensitive pen on a screen, the distance between 2 points is measured in pixels, and that pixel distance is automatically transferred to a database, which is done at several points in time. So the experiment starts at day 45 in the rat's age, then at days 50, 60, 70 until day 110. In principle, 7 measurements are collected. And I say in principle, because you see that some rats do not make it to the end of the study. And that is because they are sometimes not surviving anesthesia. So some profiles are a little bit shorter. We see here the rat profiles. We see a trend. At the same time, we see some variability because of just rat to rat variability, biological variation, but of course also some imprecision due to the measurement process. You see some curvature, and that is because, well, over a period of, let's say, 50 or 60 days, human beings grow linearly. But rats, in their short lifespan and their quick growth curve, you already see the growth, the form of the shape of the growth curve, the curvature. You see that very clearly. And that's why we will have to transform the data a bit to make them linear. Now, as I said, there is rat-to-rat variability. How are we going to capture that? I think a very standard approach would be to say, okay, I will have the effect of time. I will have the effect of group, low dose, high dose, placebo. But these are fixed effects. That's the way we call it in random effects modeling. But at the same time, there is a rat-specific component in the evolution. And in the upper left corner, I have accommodated that using a random intercept BI. And then, of course, as I said, apart from the rat-to-rat variability, there is a measurement error, and that is why we have our good old epsilon term, epsilon ij. I being the rat, J being the measurement occasion within the rat. And of course, once again, this is all very standard mixed modeling theory. So if you think this is basic, yes, it's basic, but I would like to repeat it for a very good reason. So in the spirit of that so-called hierarchical model, which we have at the upper left corner, the random effect is assumed to be normally distributed. That's what we commonly do. The error term is assumed to be normally distributed, which of course means that my beta parameter is unrestricted, but sigma square and D, having the interpretation of variances, should be non-negative. It's even best that sigma square is positive. Of course, we know that a hierarchical model implies a marginal model. I can integrate over the random effects. It's as simple as that. And integrating over a normal random effect, if it enters the model linearly, is extremely simple and produces the upper right model, which is a multivariate normal with a structured variance covariance matrix, which we call, for example, compound symmetry. That's a common name that we use for this model. And of course, if we have a multivariate normal, once again, the mean vector is unrestricted, but the variance covariance matrix should of course be positive definite. And of course, that's all very standard, but the blue condition hierarchical is stronger than the red marginal condition. The marginal condition is actually simply that D times the matrix of ones plus sigma squared times the identity matrix is positive definite. So it's perfectly possible in the red marginal condition that D would be slightly negative, sigma square sufficiently positive, and you would still have a positive definite matrix. So that would mean that in that case, there is no hierarchical interpretation, but there is a marginal interpretation. Even though that has caused confusion for decades, it's nothing new. This is absolutely nothing new, but it does have implications. If you think about it, I can, for example, test a null hypothesis whether D is equal to 0. So I will say that again. I can test a null hypothesis whether D is needed, yes or no, whether, in other words, a random intercept is needed, yes or no. But of course, from our basic statistical knowledge, we say, okay, you test for D is equal to 0. I can do that one-sided or two-sided. But then I say, wait a minute, two-sided, it means the null hypothesis is D is equal to 0. So it can be in the alternative space, positive or negative. evidently. I can also choose to test one-sidedly, so it's 0 or it's bigger than 0. But in the hierarchical space, in the hierarchical framework, it's even more different, because there you say I can test one-sided or two-sided, but it's the same thing because there is no left-hand space. So the parameter space on the left-hand side, because of the restrictions, is a half line for D. But in the hierarchical space, it's not a full line because there are some constraints by sigma square, but at least the null hypothesis is not on the boundary of the parameter space. So this has given rise, and already way back when, in the 1980s and the 1990s, work by Stram and Lee, Self and Liang, to the so-called mixture testing problem. That is, if you think about it, you have your likelihood. And by the way, on this graph, the tau square is actually the D from the previous slide. It's the same thing. So in the parameter space, you can say, okay, if 0, the null, lies to the left of the top of the mountain, think of, for example, the Sugarloaf in Rio de Janeiro is that kind of mountain. If it lies to the left of the top, then of course you can move in the direction of the alternative. But if the null lies to the right of the top, it basically means that negative values are not allowed. The alternative space is pointing to the right, but all likelihood values to the right of the null hypothesis are less elevated than at the actual top. So you're not going to move. The null and the alternative is the same in that case. So because under the null, case A and case B have the same probability of occurring, what you get at the end of the day is that the test statistic for D is equal to 0, the likelihood ratio test statistic doesn't follow a chi-square asymptotically, but it's a mixture of a chi-square with 1 and a chi-square with 2 degrees of freedom, with 50% chance for each of the two mixture components. That's been well known. It's for one parameter. It happens for more parameters as well. We have extensions for matrices rather than a single variance component. You can have a random intercept, a random slope. It all extends. And here Verbeke and I have shown this is not only true for the likelihood ratio test, it's also true, and you would hope that, for the score and the wall test, which are known to be equivalent under the null in case that there is no boundary problem, but when the boundary problem happens, that is the case. So, as I said, the case where you have only one variance component is not the only one. Unstructured, that means you have a matrix, you have a structure with k random effects, null, versus the alternative where you have k plus 1 random effects, alternative. In that case, the null distribution is a 50-50 mixture of a chi-square with k and a chi-square with k plus 1 degrees of freedom. In a variance component model, where you say, okay, I have a number of random effects, but like in agriculture, we have models like that often. We have, for example, k random effects, but they're all assumed to be uncorrelated with each other. In that case, we also have a nice closed form for this mixture null distribution. If you test for k versus k plus k prime random effects, and then it's actually, let's call it a binomial sum of chi-square distributions. If you say, hey, wait a minute, if you want to test in the unstructured case, k versus k plus k prime random effects with k prime greater than 1, okay, it's also a mixture of chi-square, but with non-constant coefficients, and there is no simple closed form for that. So then the only thing you can do is a Monte Carlo exercise to find out the null distribution or the p-value equivalently. So, okay, let me apply this theory to the red data to illustrate. So, yeah, as I said, I'm going to linearize time. So I'm not going to use h, but I'm going to use this transformation, the logarithmic transformation of h, so that I make the profiles linear. The model that I'm considering, the biggest model that I'm considering has, of course, an intercept, and that intercept, fixed intercept, is the same for all groups. because at the beginning of the experiment, there is no randomization yet. Then I have a group-specific slope, a random intercept, and a random slope in time. Okay, that's model 4. And in model 4, I have a random intercept, a random slope, as I just said, and these two are allowed to be correlated. Model 3 says, no, they're both there, but they are uncorrelated. Model 2 says, no, there is only a random intercept. And that is the one that we looked at before, that marginally produces compound symmetry. And then I can consider model 1 with no random effects. You clearly see what's happening. Model 1 is nested in model 2, is nested in model 3, is nested in model 4. So, for example, here is the estimates. Now I can do the estimation for the variance components. So that's clear. I can do that one-sidedly, or I can do that in a two-sided fashion. So in model 1, I clearly have no random effects, and it's relatively easy. In model 2, I allow in the one-sided case, the variance has to be positive. In the two-sided case, it's allowed to be negative, but okay, if it's estimated positive, that's what it is. In model 3, I have two variance components that are independent of each other. So in the one-sided case, I'm actually estimating my second random effect to be equal to 0, because I'm on the boundary of the parameter space. But if I free myself of that consideration, I get a negative second variance component. And in the fourth model, where I assume them to be uncorrelated, correlated, not uncorrelated, I actually get a similar phenomenon. So in models 1, evidently, and in model 2, the two approaches, one-sided and two-sided, provide me with the same result, but in model 3 and model 4, they are actually slightly different. So if I now compare model 2 to model 1, again, model 2 has this single variance component with variance estimated to be 344. The likelihood ratio test statistic is 174. The score is a bit smaller. That's not uncommon. The wall test is even smaller. But the p-values are different. Now you may say, I don't see that. And of course you don't see it if I denote it like this. But the reference distribution is a little different. So if you would basically look at the decimal expansion, you would see a difference. But it's much more clearly the case if I compare model 3, where I even have a different estimate to model 2, different estimate and different null distribution. In that case, what I see is that the p-values are equal to 1 in the one-sided case, because null and alternative are the same. But in the two, that's indeed true. The null and the alternative are the same here in this case. So if I go to the p-value in the two-sided case, it's different, very different. But of course, in all cases, it's still non-significant, so it would not lead to a different conclusion. If I compare model 4 to model 2, and I can do that, model 4 to model 2 is you remove one random effect, but that it follows a mixture of a chi-square with 1 and 2 degrees of freedom. You also see here that you have a very different result. In a way, everything that I've shown, not everything, is very standardly known, but it's that confusing thing that in hierarchical models, you have also a marginal interpretation. The marginal interpretation, yeah, it doesn't allow for the random effects interpretation anymore. That's a limitation. But you have a broader parameter space in the sense that negative correlation is also possible. Now, in some experiments, let's say growth curves, a random intercept with a negative variance, so that would mean negative correlation would not make sense. But there are settings where a negative correlation does make sense, where you have clusters within which there is competition. Let's say I take rats, I put them in a cage. Some rats I give them food, but not enough food for all of them. So some rats will dominate and will eat most of the food. at the expense of the other rat. So if I then start measuring weight, if one rat really has a high weight, I know because there is starvation, there is limited resources, some of the other rats will be relatively low in weight, and that may induce negative correlation. So an extended framework is indeed important. Now, what I've been saying so far is, and I would like to go back a few slides and then move forward again, but that is, okay, if I have a marginal model, let's say the random intercepts model, when I go to, or rather I should say the compound symmetry model. So if I have a compound symmetry model, I can say the following. If sigma square and d are positive, then there exists a hierarchical interpretation. But if sigma square is positive and d is negative, and yet it's positive definite, there is no hierarchical interpretation. And that's a little bizarre. And we've always accepted that, but it doesn't need to be the case, because what we now can do is put the assumptions that we make for the error component, for the random components under a magnifying glass. And we say, hey, traditionally, we assume that the random intercept bi and the measurement error terms epsilon I1, etc., are independent of each other. But let me break that. Let me break that logic and say the random intercept and the measurement errors are correlated. And I give them a correlation or a covariance parameter tau. That's uncommon. We don't do that usually in mixed models, but I'm going to do it anyway. The random intercept has its variance d still. The measurement error has variance sigma squared, and then the measurement errors are independent of each other, but all of them are correlated with the random intercept. Okay, I can even derive the conditional distribution of the errors given the random effect from it. And what should be clear right now is I can write down this model, but the parameters d, tau, and sigma square are not individually estimable. So I cannot separate them based on the data. So is this then a silly exercise? I don't think so. Let's come to that. So the implied marginal model, as I said, consists of d plus 2 tau times the J matrix. And again, the J matrix is the matrix of ones. And so d and tau factor into the J matrix. Sigma square is still multiplied with the identity matrix. Okay, this is our new, funny, bizarre model. You may call it what you want. If I go back to my conventional compound symmetry model, you say, no funny things, just a parameter in front of the J matrix and another parameter in front of the I matrix, the identity matrix. And of course, if that's two ways of looking at the same model, you would identify the parameters and say sigma square is eta squared. That's fine. But of course, clearly d plus 2 tau, that's equal to lambda square. Lambda square is identifiable. D plus 2 tau, therefore, is identifiable, but not d and tau separate. Okay. Now, that means there is no unique solution for d, but you can actually spell it out and say, let me rewrite this a little bit, such that the parameter that's not identified becomes a tuning parameter. I'm going to rewrite it such that that parameter alpha can vary between -1 and +1. And 0 would, of course, correspond with a more conventional model. But again, what is that now? A model where I have a parameter that is not identifiable? Well, we call that a sensitivity parameter. So we can do some sensitivity analysis and say, okay, the variance of a measurement can be expressed in my new parameters. The covariance can be expressed in my new parameters. I can even at the end of the day do empirical Bayes predictions. And you know what the empirical Bayes predictions are. These are the posterior values for the random effects. So for example, BI a priori follows a normal with mean 0 and variance sigma square, but BI hat, so a posteriori, has this expression. And you see that even though D and tau are not identifiable, jointly yes, not separately, the choice of d and tau does influence the empirical Bayes estimate. So what it tells us is that the classical empirical Bayes estimate, where usually without thinking we take it for granted, actually has more than one possible form. Okay, so that's that. Let's now look at a few examples and see what this gives in reality. And for that, I will quickly run over a few additional examples. Let's take a toenail data set, a clinical trial where the outcome is binary. So people are infected with the fungal infection in their toenails, which leads to discoloring of the nails. People are then giving an antifungal treatment. The only problem is they need to take that treatment for 3 months, and there is a risk of non-compliance, of course. So we have 2 groups of 189 patients randomized over 2 treatment arms and split over 36 centers. And we follow the outcome, which is actually, in this case, length of unaffected toenail, Yij, and we give that model a random intercept, a subject-specific effect, and then an evolution over time, which is different for the treated group. So T is equal to, capital T is equal to 1, and the untreated group, capital T is equal to 0. So beta 0 and beta 1 are the 2 intercepts for each of the 2 groups. Beta 2 and beta 3 are the time slopes. Okay. This is still the conventional mixed model with parameters lambda square and u square having their usual meaning. Lambda square, the variance of the random intercept, nu square, the variance of the measurement error, and they're both positive. So that actually means that this is this is actually a positive correlation problem, a classical problem. Second example, the National Toxicology Program data. We have rats that are exposed to a toxic agent, ethylene glycol in this case, and the rats are pregnant. Now, exposure to ethylene glycol, that happens in 4 dose groups, going from placebo, nothing, to the highest dose group. And then the rats are pregnant, they produce a litter, and that litter typically contains somewhat between 2 and 16 fetuses. And for each of these fetuses, we score whether they are malformed, yes or no. That's the outcome. So we built a relatively simple model. Ethylene glycol is a compound. DHP is another compound. There are several compounds that we can study. But at the end of the day, an outcome that we will look at here is actually a continuous outcome, birth weight of the fetuses, and we let that depend on dose, of course. The idea is that the higher the dose, the lower the birth weight. Bingo, that is correct, because we have a negative dose parameter here. But then, of course, we want to look at the variance of the random effect, BI, and the measurement error variance. And what you see is that both variance components, again, they're small, but that has to do with the scale, but also they are positive. Third example, this is also a toxicology example. It's actually a heat shock study. So we again have pregnant rats, but we're going to examine the effect of exposure to elevated temperature. So fever, we basically mimic fever, or in this experiment, fever was mimicked by explanting the fetuses from the uterus, put them in a bath, in a bath with hot water, warm water, from 3 to 5 degrees temperature elevation for a certain amount of time, ranging from 5 to 60 minutes. So Yij is a continuous outcome. For example, crown rump length, head circumference, etc., things like that. So the covariate effect of interest is actually the exposure, and that exposure is the product of temperature, elevation, and time of exposure. It's a volume of exposure. But we do have also a main effect of time of actually no, of temperature. So there's a main effect as well, but that main effect is of course only playing when there is elevation above zero. Good. What we see at the end of the day is that in this case the random intercepts variance component, I now have to say, is estimated to be negative. And of course, you see that it's not significantly different from zero, but I still would like to see, okay, significant or not, can I give it an interpretation? And that's what we do here. So what we see on this slide is actually by n, the maximal cluster size. That's just an indication. And then the nu square is sigma square is the measurement error variance. Lambda square is the estimated in the previous slides variance component for the random intercept, positive in onychomycosis, positive in the NTP study, negative in the heat shock study. And then, as I said, we can rewrite the lambda square as the sum, and I go back for that a little bit. The lambda square is actually estimated here. Lambda square is rewritten as d plus 2 tau. But we do that with that parameter alpha. The parameter alpha can always go from -1 to +1. And somewhere down the line, we pass through a point where the parameter is actually going from this additional parameter tau. And remember, the tau is the covariance between the measurement error and the random effect, the random intercept in this case. Somewhere down the line, that tau is passing via 0. And at 0, look where we are at 0. There, d is somewhere between 6.3 and 7.4. And that's exactly where we pass through this value. So 6.49 is a possible value for d, located here. And that would correspond to tau is equal to 0. And as a consequence, the correlation between measurement error and random intercept would be 0 as well. In this case, when the alpha is smaller than -0.3, say, we get a positive correlation between measurement error and random intercept. At the other side, it is negative. But the thing is, all of these stories are equally likely from a likelihood perspective. They fit the observed data equally well. So the marginal model is exactly the same, because whatever you do, it produces marginally 6.94 and 6.49 for the variance components, but the hierarchical interpretation, including the empirical base estimates, would be different every time. Same story for the NTP data. See, the lambda square is, let's say, 59. Actually, that's why we plot here not d and tau, but 100 times d and 100 times tau. The 59, where would we get through 59? Here. And that's also the point where you go again from a positive tau to a negative tau, from a positive correlation to a negative correlation. So that is the special case where the correlation would be equal to 0. And that indeed is the case where the conventional case where random intercept and random slope would be uncorrelated. It's the standard conventional model, like most linear mixed models are written, but it's only one of the many possibilities that we have. In the heat shock study, though, as we said, the lambda square is actually negative. So that means if you look at the correlation, let me go back to NTP and onychomycosis for a second. I said it already, but let me repeat that you always go from a positive correlation to a negative. And of course, if you're in a continuous function, you pass via 0 in both examples. But if the variance component lambda square is equal to a negative number, the correlation here is negative. In absolute value, it starts to go down. And then it starts to go up again, and you end up where you were. So you never go through 0 in this case. That means this model in the conventional way doesn't exist as a hierarchical model. But in our extended space, it does exist, provided that you acknowledge that there is a certain amount of competition happening in this data, which is not your standard conventional approach. Okay, good. Let me go one step further and look at the over and under dispersion right now. So for that, I will be looking at another study, one in counts, the epilepsy study. So I have 45 patients receiving placebo, about the same number receiving a new anti-epileptic drug. And it should be understood that placebo actually means just standard therapy. All people get therapy, but the placebo patients, they actually get nothing but their standard therapy. And the active patients, they get a new anti-epileptic drug as well. So after a run-in period, people are followed up for 16 weeks. Some even 27 weeks. And every week we count the number of epileptic seizures, so clearly a count. Excuse me. We have a view, a perspective on the data here. So at the top we see the profiles for the placebo group. At the top left, at the top right, we see it for the active group. And what you do see is that there is quite a lot of activity at the bottom of the plot, which means that many patients have relatively no numbers of epileptic seizures. On the other hand, some people really do have very high numbers and are highly variable, shooting up and down all the time. So, okay, that gives us a perspective on the data. Now, the data are longitudinal because we measure these people in the base clinical trial for 16 weeks in a row. So we have 16 repeated measures per subject if they don't drop out. But just imagine that we start more gentle and we say, if you have a single count, what would you do? You could consider the Poisson model, but we all know the Poisson model is a beautiful mathematical model, but a bit restricted. It sets the mean and the variance equal. Now that's a nice property of the Poisson model, but the data don't always know that they have to follow the Poisson model. And therefore, you may have a mean and a variance that actually happens to be different. Of what can we do then? Well, over dispersion, of course, we can include an over dispersion parameter and say the mean variance relationship from the Poisson is relaxed. We add an additional parameter, an over dispersion parameter, quasi-likelihood. In a two-stage approach, you say, okay, what I'm going to do is work with random effects, but in a bit of a different way than we did before. We say the outcome Y, the count, and again, for a moment, this is univariate, a single count per person. The count Y is following a Poisson given its parameter, but that parameter is not a constant, or it does not depend on covariates only, it's subject specific. So it follows a distribution with a certain mean mu and a variance sigma square. That in itself is enough. Say, okay, the lambda is a random variable with a mean and a variance, finite mean and finite variance, to derive from there with iterated expectations, and the same for the variance, that the variance is actually no longer mu, but mu plus sigma square. But mu plus sigma square, that means over dispersion, not under dispersion. Now, what if I let that sigma square to be negative? What should I do? Question mark. Okay, that's now a question a bit similar to what we have in the first part, but now for Poisson. Now, as I've said a few times, the data are longitudinal. So it's not enough to say what I can do with a single measurement. I should expand it and look at multiple measurements. So I'm going to look at the entire sequence of 16 repeated measures, say. But of course, what I can do for a single measurement, I can do 16 times. So I don't get a lambda parameter, I get a vector of 16 lambda parameters. I assume them to be distributed according to a certain distribution. So that means I have a mean vector and a variance covariance matrix. Now you may say at this time, if you put a distribution on the lambdas, either on the previous slide or here, what distribution? Because you give the mean and the variance, but you don't give the entire distribution. True, I have not done that yet. And the calculations that I'm doing do not require the distribution to be specified. I can calculate, for example, the marginal mean and the marginal variance covariance matrix without any trouble. Okay. Now, of course, I can generalize this and say this I can do for counts, but there is no reason why I should restrict myself to counts. I can do that for the entire exponential family and therefore for the entire class of generalized linear models. But before I do that, let me go to the classical so-called generalized linear mixed model. In a generalized linear mixed model, you claim that every outcome, so every measurement for every subject, follows an exponential family distribution that you choose, and your natural parameter theta is given a the natural parameter actually is given after transformation a linear predictor. That's what I wanted to say, with fixed effects and random effects. And in the spirit of Breslow and Clayton and several other people, Wolfinger and O'Connell, who worked on this, the random effects are also assumed to be normally distributed. Let me apply that to the specific case of counts. In that case, Yij would, for example, follow a Poisson given lambda. The lambda is given a linear predictor, of course, after log transforming it, and the linear predictor contains random effects that are normally distributed. Now, maybe it's good to say here, how does that connect to the previous slides? The previous slides did something else. They accounted for overdispersion by making the lambda parameter random, explicitly giving it a distribution with a mean and a variance, but I have refrained of giving you that distribution in detail. Here, we basically started again. We said, I will build a generalized linear mixed model. And yes, the lambda will contain a random effect. So we make it random, but basically by putting a normal random effect on its log transformed value. So it's not dissimilar in spirit from the previous approach, but it's different still. I can calculate, and that's a bit contrary to common belief, I can calculate from this model its marginal moments, the mean and the variance. And then you say, okay, if I look at that mean, and then I look at the variance is equal to the mean. And how should I interpret that? Well, it's of course a vector. There is a mean vector mu I with components mu ij. I can place that vector into the diagonal of an identity matrix. So you take the ones out and you put the mu ij's in. MI, in other words, is a diagonal matrix with mu ij along the diagonal. But then you see that this expression, and it's clear in the multivariate case, but it's even clearer in the very specific case where you have a single measurement per subject, you see that the variance is the mean plus something else. If I go back to the first attempt, I said the variance is the mean plus something else. And that something else was clearly non-negative unless I apply a trick like in the first part of the presentation, and that is allow it to be negative. Well, same thing here. E to the power d minus 1 is always greater than 0 if d is positive. That's clear. But I can do once again the same thing. I can allow that d to be negative, and then you would actually get a reduced rather than an inflated variance. Good. Now, we seem to be going back and forth between two approaches. One was to put a distribution directly on lambda. The other was to put a distribution indirectly on lambda by integrating a random effect into the linear predictor. What we will now do is we will do the two at the same time. We will have that direct random effect here. It's operating the theta ij. Now, I needed to change notation a little bit, but the theta ij is the direct random variable that is sitting on lambda ij directly in a linear fashion. But the BI is the normal random effect, which I can integrate after log transformation. If there is no theta, then it's the generalized linear mixed model. If there is no BI, then it's that first approach. Now, it's a bit annoying to talk about that first approach. I should be giving it a different name. I will do so almost immediately, but not now yet. I say now I have two random effects in my linear predictor, one normally distributed, the other one with a certain mean and a certain variance function. Also here, I can derive the marginal moments, marginal mean in the general case, marginal variance covariance matrix in the general case, or I can specify it explicitly for the case that I have a single measurement. And once again, you see in all cases that the variance is equal to the mean plus an additional term. And the only thing we can say is that additional term gets more and more complicated as we put more and more stuff in the model, of course. Okay, now, fully parametric specification, that first approach with the distribution with the mean and the variance that I don't specify, let's stop that game and let me come out with a choice. But why was I playing that game? Because it's not unique. I'm not going to say this is what it should be and always should be. That's not true. That said, it makes sense to put a gamma distribution on it. And I think some of you have been guessing that or knowing that it would be the gamma distribution. Why? Well, first of all, the theta should be positive because the exp of something is positive, the lambda ij is positive. So to keep lambda ij positive, the only way of doing that is keeping the theta ij positive. The gamma distribution, of course, lives on the half line. So bingo, that does the job perfectly. But there is another reason. The gamma distribution, as we know, is conjugate to the Poisson distribution, and that makes our life a little easier. It helps us in deriving, for example, closed forms, marginal means, etc. So we call the model Poisson gamma normal. Now there are two special cases, actually three. The Poisson gamma normal contains a gamma random effect and a normal random effect, and now it's easier to talk about it. If it's only the gamma random effect, the Poisson gamma, of course, you know another name for that. That's the negative binomial. The Poisson normal, you know another name for it. That's the generalized linear mixed model. So this model is a super model sitting on top of both the negative binomial and the generalized linear mixed model. Okay, let's apply it to the epilepsy data. So let's look at the bottom of the slide first. What we are going to do is say, okay, my model has an intercept and a slope in time at the log scale, of course, and a random effect B, which is normally distributed. But there is also that additional random effect theta ij, which is given a gamma distribution. And let's say it's a gamma distribution with parameters alpha j and beta j. All right, because of the nice properties of my of the conjugacy, the marginal model, hey, but it is not a marginal model. No, it's true. It's a partially marginalized model. I marginalize over the gamma random effects only. You get this expression. And if that expression looks vaguely familiar, but not entirely, that is because it reminds us of the negative binomial model. Now, marginalizing over the gamma random effect is relatively easy. Marginalizing over the normal random effect now, because the normal random effect is actually sitting into the exp function, which I denoted by kappa, but that is sitting here and there. That's not easy. It's not possible to do that by hand. And if it's possible, it would be very difficult. Therefore, what we are going to do is we're going to basically marginalize numerically, and that can be done in the SAS procedure and mixed without too much trouble. Okay, let us see what this gives to my data analysis. So I have my intercept and slope in the placebo group, intercept and slope in the treatment group. And I'm considering four models. The combined model at the bottom right, that is the Poisson gamma normal. The Poisson model has none of the two random effects. The negative binomial, only the gamma random effect. The Poisson normal, only the normal random effect, and the combined model as both. Now, you might say, is there any reason to include both random effects? Because it's not because you can do it that it's a good idea. Maybe, yeah, it's a nice mathematical thing to do, but you're making life difficult. It doesn't add any value to the data. Well, of course, the proof of the pudding lies in the eating. We can look at the, let's say, comparison, have the combined model versus its two neighbors to see whether it's a significant improvement, for example. But I would like to, and it is, but I would like to look at a few other characteristics. One characteristic is, okay, what is the correlation between two measurements of the same patient? Of course, the correlation with a linear mixed model is relatively easy to derive, but with a Poisson normal model, it's a bit more complicated because there is the mean variance relationship, etc. So therefore, it's not a constant. And on top of that, here we have the gamma random effect. Okay, let's calculate the correlations then. We know it varies with time pair and with treatment group. So let's calculate all of them, see what is the largest and the smallest. And then we see in the Poisson normal case, the correlation is roughly 0.85 to 0.9. So very high correlation. In the combined model though, the correlation decreases to, shall we say, roughly 0.30 more or less. So much smaller. So what's happening here? What's the problem? Well, the thing is, in the Poisson normal model, I have a normal random effect only. Now that random effect induces overdispersion, and that same random effect induces correlation. But if with a single parameter, with a single random effect and its variance component, you have to describe a correlation function and an overdispersion component, it may simply not work. You're asking two jobs at the same time from the same parameter. And it's all nice and well when you have a sufficiently small overdispersion and a small correlation. Or both are large, then it's also fine. But here we are in a situation that the repeated measures are relatively weakly correlated, 0.30, 0.31, 0.34, 0.23. But the overdispersion is high, and it's not possible for the model to capture both satisfactorily. So you find a bit of a compromise between both. The combined model doesn't do that, it separates them. So in the Poisson normal model, you have a single parameter that basically tries to capture a high correlation and a low overdispersion. It's the other way around, a high overdispersion and a low correlation, but it doesn't work very well, and the correlation is therefore overestimated. In the combined model, and this is what I wanted to say, the theta ij are assumed to be following a gamma distribution, but I can perfectly allow them to be uncorrelated with each other. So the theta ij's, because they are uncorrelated, they capture no correlation whatsoever. They only capture overdispersion. The normal random effects, they still carry both overdispersion and correlation, but that's great. Because if there is a small correlation and high overdispersion, the normal random effect will have a relatively small variance. So that variance will be too small to capture all the overdispersion, but the gamma random effect will compensate for that, and therefore it will basically, I will be able now to estimate a small correlation and a high overdispersion at the same time. There is no reason why the correlation and the overdispersion should be both large or both small. It could be, but it doesn't have to be the case indeed. All right, so we have done what we needed to do here. There's another thing. You may say, oh, okay, it's all nice and well that you basically get your correlation right, but what I really would like to know, is there a treatment effect, yes or no? And look at this. I can look at the treatment effect additively, or I can look at it multiplicatively. No treatment between means the difference between the slope parameters is 0 or their ratio is equal to 1. In the Poisson model, which is not a good fit, both of them are significant. Hooray, but it's not a good model. The Poisson model, if you would go for the multiplicative effect, would tell you that there is a marginally significant effect. The negative binomial model would do the reverse. There you would only have a significant effect with the difference, so with the linear hypothesis. And in the combined model, both of them are non-significant. Now, what does it tell us? What we usually would do, I think, on data like this is fit a Poisson normal model. That's what many people would do. And if you would test your hypothesis multiplicatively, you would think that you have a, let's say, not so strong, but still significant effect. Whereas in the combined model, you would say, no, that is no longer the case indeed. So to conclude at this point, in the epilepsy data set, as I've said before now several times, we have moderate correlation, we have strong overdispersion, and we are now able to capture that with our combined model. But of course, there are other correlations, other situations, strong positive correlation and mild overdispersion, and sorry for the typo, that's the other way around. And then again, you need to go to negative values. And there we have seen that this model is not the best to do. You basically should go to alternative overdispersion model. So at the end of the day, we would like to deal with whatever correlation and whatever underdispersion. And for count data, we have made good progress in that sense. All right. What people sometimes also say is, okay, now you have your extended model, but are you so sure that it fits the data well? Of course, not until you check it. What you can do is the usual thing. You include more effects, fixed effects, for example, and you check whether they are significant, yes or no. And if they keep coming back non-significantly, maybe you've properly specified the model. We've also done alternative things, and I will not discuss it in detail now, and that is local influence, for example. Try and find out whether the model doesn't get fooled by a few influential subjects, for example. And that's actually the case. It is the case because we essentially have three types of patients. People with a relatively low number of epileptic seizures week after week, people with mild conditions, which is of course favorable for them, and that's a common thing to happen. One, we have people that have much more epileptic seizures, but then there is a small group of people who at some points in time have high correlation at other, high numbers of epileptic seizures. At other times they have low numbers of epileptic seizures. And that is because their epileptic seizures are many, but they're relatively mild. And the rhythm of epileptic seizures doesn't necessarily follow the 24 hours rhythm. So if you have a lot of seizures, but it's not very clear, and you don't wake up over it, it may well be that for a period of time, your epileptic seizures go unnoticed over the night. And unless you have a capturing device, we would not see that. So for a while, it looks like there is almost nothing going on. And then it moves back into the daytime rhythm, and you would see for these people for a certain period of time a high number of epileptic seizures. These people are different, and they actually have a strong impact on the correlation structure. And then we have seen that taking them away from the data set or considering them a separate group does indeed change the fit and the conclusions once more. But I think on that note, I've discussed what I wanted to discuss. The notes are available if you want. I did include a few ramifications that are not going to be discussed now in the interest of time, but you get, I think, the main ideas. So on that note, let me from my side thank you already very much. And I'll be very happy if there are to ask questions. Or sorry, you can ask questions, I can answer questions, sorry.
Thank you very much, Dr. Geert, for your excellent talk. Por favor, vamos a abrir la sección de preguntas. Quien tenga una pregunta, por favor. I have a question, but it's it's a comment. I had a question, but I don't know if it's how is the convergence when you are working with the SAS in this kind
yes.
of?
It's a very good question, Mercedes, because we were actually worried prior to doing it for the first time when we were developing the model, doing the equations, etc. We had the idea of doing it in SAS in this way, and that was actually Geert Verbeek's idea to do the estimation in this way. But we thought, okay, two random effects at the same time in a relationship that is, of course, not linear, because otherwise it would be an issue. How is this going to work? We were surprised by the very good convergence properties. And by the way, you can program it up very easily in the SAS procedure NL mixed, or in the R function NLME. It's not very difficult to do, because the difficulty for the software would be dealing with the gamma random effects. But since we integrate over them, the only thing that SAS gets to see is a model with normal random effects. But then still, the issue of convergence, we were a bit nervous about it, but we saw at the end of the day that the convergence properties were, for count data, let me say that, for count data were extremely good. Now, there is a similar version of and the model, the combined model that I have been developing here is joint work again with Geert Verbeek and with Clarice Demetrio from USP, University of São Paulo, Universidade de São Paulo in Brazil. So also in the time to event case, in the survival case, it works rather well. But in the binary case, where you can also do it, their convergence is a bit more difficult. And one of the reasons is that over dispersion in binary data is a very different phenomenon than in count data. The reason is in count data, univariate data, simple univariate data can already show over dispersion. You calculate the mean of counts, you calculate the variance of counts, and if it's very different, you may need an extended model versus the Poisson model. On the other hand, if you have binary data follow a Bernoulli model, unless there are covariates. So it's the variance is pi times 1 minus pi, and that's it. There cannot be over dispersion yet. So for binary data, there is a stronger relationship between correlation and over dispersion. And there you really need a lot of data to stabilize the calculations. If you have, let's say, binomial data rather than binary data, and what does that mean? Like at every measurement occasion, a binomial experiment is conducted with repeated binary data rather than a single binary data point, then yes, it becomes more stable and the convergence is becoming easier as well. But for count data, if we return to your question, for count data, we have seen uniformly that convergence is relatively, actually not just relatively good, it's actually excellent.
Oh, thank you very much, Dr. Geert. ¿Hay otra pregunta? Then, Dr. Geert, we are very, very grateful with you. Thank you very much for your excellent presentation. And we are really was an honor to have you in the event.
Thank you very much, and I wish you all the best with the rest of the conference. Take good care.
Thanks again.
Ciao.
Ciao.